Welcome back. Today we're going to be looking at logarithmic properties. What might be one of my favorite sections in this whole class is the properties of logs and how to expand and condense logarithms using three basic properties. It's a little bit longer of a section, but we're going to try to get through them all, so let's go ahead and get started. All right. The first property of logarithms that we're going to use is this expansion property of multiplication, or the product rule for logs. You'll notice that if you have a multiplication on the inside, it turns into addition on the outside where we split up the log. Now these properties come right out of the exponential properties, or the properties of exponents. So if you think about exponents and multiplying and adding, you'll remember there used to be a property, and maybe I can even use the same basis, of b raised to the m plus n is equal to, you'll remember b raised to the m times b raised to the n is exactly the same thing as b raised to the m plus n, right? And so what you see here is you have multiplication on the outside of the bases, multiplication outside of the exponent, turning into addition on the inside of the exponent. Well, it's flip-flopped now. Now we've got multiplication on the inside, turning into addition on the outside. So it's the inverse property. I'm going to leave that up there. It's the inverse property, but flipped for logarithms. And so we're going to expand this as much as possible, even though it might not even be productive for the future. We're still going to do it. So you see a multiplication there. So the first thing we're going to do is expand this log, keep the base exactly the same, 8 plus log b of k. That's a nice pretty answer, but we could expand it even more because you know 8 is technically 2 times 2 times 2, right? And so what I'm going to do is I'm going to split that 8 up into 3 different addition problems of 2 times 2 times 2, and expand it to log b of 2 plus log b of 2 plus, there's another one, log b of 2 plus, keep that k in there, log b of k. So anytime you see multiplication on the inside, you can expand the log and put addition on the outside. Now it's pretty similar in a pretty similar way. If you see division on the inside, it turns into subtraction on the outside of an expanded log. You'd be like, does that fall in line with the other rules we've learned? Well, yeah, you remember the exponent property of b to the m over b to the n, and you subtract the exponents. You've got right here division on the outside turning into subtraction on the inside of the exponent. But now we've got division on the inside of the log turning into subtraction on the outside of two logs. So this one has a lot going on. We're going to try to get it all. We're going to expand it as much as possible. The first thing we're going to do is hit that division, though, because that division sign is touching literally every term. So the first thing I'm going to do is expand the log with division, and then we'll hit it with some multiplication. So log of 7x2 plus 21x minus the bottom log of 7x times x minus 1 times x minus 2. You might be asking yourself, well, could we apply the multiplication rule that we just learned to the same problem? We absolutely could, and we could probably do a lot with it. Before we do that, though, I think I'm going to factor out some common terms right here and rewrite it as log of, I think we could pull out a 7x, parenthesis, x plus 3, minus, keep all the same minus there, 7x, x minus 1, x minus 2. And here we're going to be able to expand this a lot. So every multiplication problem you see with every factor can get turned into addition, and the only thing we're going to be careful about is that minus sign in the middle. So we're going to go log 7 plus, because there's a time sign right there, log x plus log x plus 3. And now here's what I was saying, you need to be careful with this minus sign, because when we expand this, that minus sign is going to get distributed to every term. So we'll have another log 7 plus log x plus log x minus 1 plus log x minus 2. And when we distribute that negative sign across every term inside, so there's 4 terms there, we'll end up with log 7. Might just do this. Oop. That negative sign is going to get distributed, so we're going to have a negative, another negative, and another negative. And we'll see some terms end up canceling out. So log 7 minus log 7 goes away, log x minus log x goes away, and we're left with log x plus 3 minus log x minus 1 minus log x minus 2. And it might be tempting somewhere in there to try to expand an addition on the inside, but we don't have a rule for that. So see this addition and subtraction, subtraction. We do not have a rule for expanding addition or subtraction on the inside, so don't be tempted to try and make it happen when that's as far as we can get for that expansion. You'll notice if you would have factored out and canceled out some terms, so maybe like you factored out a 7x way earlier up here, and you ended up with x plus 3, you'll notice the 7x's cancel out, and that was the same canceling we did with the subtraction. So mathematically, whether you did it right there or you did it at the end, that same canceling would have happened. Those red slashes down at the bottom, those would have happened at the beginning of the problem or the end of the problem, and you're welcome to do them in either spot. All right, let's keep going and look at the power rule. This power rule is very similar to the other power rule. It might look a little different, but if you have your base raised to the m raised to the n, we know that that's the same thing as b to the mn from our properties of exponents. And so what you see is an exponent on the outside turns into multiplication on the inside. Well, now we've got an exponent on the inside, and you'll see that you can move it to the front and it turns into multiplication on the outside. And so something you'll see people write a lot is they'll circle this and bring it out front. And that is an okay way to notate that as you're working through a problem. So I'll do the same thing here. I'll circle 2, bring it out front, and I'll get 2 ln of x. And so your answer is 2 natural log of x. Another way to look at the same problem is you could have done natural log of x times x and applied the product property. So that would have been the ln of x plus the ln of x, which is 2 ln's of x. And you would end up with the same answer whether you do it a couple different ways. All right, let's keep going. I think this one's going to apply a bunch of rules. The rule that I prefer using is the simplest one, which is to bring it out to the front. Take that exponent and bring it to the front. In order to do that, though, we need to know one little property of exponents, which is that if you have an exponent on the bottom, it's the same as having a negative exponent on the top. Negative exponents flip the fraction. So now we can just take that negative 2 and bring it out to the front and be left with negative 2 ln of x. All right, let's keep going. Try it 5, a little longer of a problem. Rewrite this log using the properties of logs into a single logarithm with a leading coefficient of 1. So what it's saying is, hey, we have a leading coefficient of 2 and we'd rather it be 1. How can we make that happen? We can reverse the rule we just learned and say that 2 can go to the inside. So we can be left with a log 2 4 squared, which is log 2 of 16. And if you remember properties of logs, is there another way to write 16 that's really cool, that works with the base? So 2 to the 4th is the same thing as 16. And now since our bases match, we just end up with 4. And so we see that 2 log 2 of 4 is the same thing as 4. There's probably another way you could work that. And this is why I think this section is so cool, is you can look at problems in a lot of different ways. What if we would have started with 2 log 2 of 4? And we would have said, hey, 4 and 2 work really nice together. We could leave it as 2 log 2 of 2 squared. See those 2's cancel out, and we'd be left with 2 times 2. Another way to do the same problem, which is why at the beginning I said this is one of my favorite sections, because there's a few different ways to get to the same answer. We got another expansion happening. We're going to be looking at all the properties on the inside and taking them to the outside. I like to do division first because I know this squared is only touching this x. And this cubed is only touching the y, and this to the 4th power is only touching the z, but that division sign is touching every single one of the terms on the top and the bottom. And so I'm going to start with division and break it apart into log of x2 y3 minus log of z to the 4th. And now we can use another property. You could start with the exponent one, or you could start with the multiplication one. I'm going to start with this red multiplication right here, because I want to get all of these terms expanded as much as possible. And so now we're left with log. Remember, multiplication on the inside turns into addition on the outside of 2 expanded logs. Log of x to the 2nd power plus log of y to the 3rd power minus log of z to the 4th power. Bring those exponents out to the front, and we've got 2 log x plus 3 log y minus 4 log z. So that used all three properties there. That used the exponent property, or the power rule, used the product rule, and it used the quotient rule. Now let's keep going. See some more expansions that we have to do. A lot of these expansions are going to be applying the properties of exponents. So if you're a little shaky on the properties of exponents, it's worth going and reviewing that. That was covered before college algebra. There's a list of 7 or 8 really important properties, such as a to the 0 equals 1, a to the negative 1 equals 1 over a to the 1/2 is the square root of a, properties like that. So if you were just to Google properties of exponents, you'd see a long list of exponent rules that are really important for applying to this logarithmic section. So the natural log of x to the cube root and squared is x to the 2/3. This power stays, and the cube root goes to the bottom, and then we can just take out that 2 over 3 and leave it as ln of x. And that comes straight out of a property of exponents that says x to the a with the b root is the same thing as x to the a over b. I'm going to leave triad 8 for you to try on your own as we move on to condensing logarithms. All right, as we condense logarithms, I think it's really important to pick the right ones first. It doesn't matter whether you start on the left or start on the right or start in the middle. What matters is that you keep your signs straight. So we're going to try to keep our signs straight as we work through this, and I am going to start with one step at a time instead of combining a bunch of things. Start with that farthest left thing, the farthest left 2 terms. As long as we keep our signs straight, we should be okay. So if we have a minus on the outside, it's going to turn into division on the inside, and we'll be left with log 3 over 4. And then I'm going to leave the rest of this exactly the same. And then I'm going to do it again, maybe a different color, do the next 2 terms. Addition on the outside turns into multiplication on the inside. So will be that blue term will turn into log of 15 over 4 minus log of x. And then last but not least, we're going to combine that negative. Remember, the negative is going to be divided, so it's going to end up on the bottom, not the top. And we're going to end up with log of 15 over 24, which we could reduce if we divide by 3 to end up being log of 5 over 8. All right. I'm going to leave try at 10 and 11 for you to work on your own to save some time, and we're going to hop down to this change of base formula. The change of base formula is a really important formula if you don't have a calculator and you need to calculate a random log, say log base 3 or log base 700, and you only have log base 10 in your calculator or the natural log in your calculator. And so what the change of base formula says is you take the argument and you take the base, and the one that looks like it's on the top stays on the top. Well, it looks like it's on the bottom, stays on the bottom, and you can choose any base in the world. Preferably, you'll be choosing base 10 or natural log as your base so that you can use your calculator to evaluate problems. So let's see. So here we have log base 0.5 with an argument of 8, and we want to convert it to natural logs. So we're going to put ln of 8 over the natural log of 0.5. And now we have a problem that we can evaluate in our calculators where we couldn't before because we don't have a base of 0.5 in our calculator. And so the natural log of 8 divided by the natural log of 0.5 is -3. And that turns a non-calculator problem into a calculator problem by changing the base. Do it one more time. Say log. It says, it doesn't tell us whether to use log or natural log. I'm going to use log so we have a different example. Log of 5 with an argument of 100 is equal to the log with a base of 10, leave it alone, of 100, because that argument's going on top and the base is going on bottom, over the log of 5. And now we can type that into our calculator. Though the top one we don't need to type in at all because we know the log of 100. 100 is just 10 squared, so it should be 2 on the top. I'm going to check and make sure though. Log of 100, 2. over the log of 5. Still can't do without a calculator. So now we end up in our calculator, 2 divided by log of 5 is 2.86. All right, so there's some basic properties of expanding and condensing logarithms and how to do it using the 3 rules, the power rule, the quotient rule, and the product rule. Thank you for watching, and I'll see you next time.